came into being. It's already there as our solar system began to coalesce and become more defined. But what I'm saying is that what is happening is something like a sink. Only I would call it a gravitational sink or a gravity sink, right? This is the solar plane over here, and so it would be like the attractive force, right, called gravity, acts sort of if it was some kind of actual maybe sink, even in terms of electric circuit or something. In other words, they sort of gravitate, you know, in that sort of idea. But this down here, this little dot, is actually up in the sun and could be represented by the core, or more than the core. It depends, you know, what percentage of the mass you want up there. So this again is, I have a little arrow drawing up. This is not that I think space-time curves down. Nothing of the kind. Space-time is flat. That's what the solar panel is here. And planets that are beginning to orbit the main star, right, are attracted toward the sun or the star as if, you know, this were true, that it was some kind of sinking and the planets were being drawn into it. But in fact, this exists in the core of the sun itself, or this is the sun itself. Okay, so that's what I'm getting at. This is not curved space-time. It's just sort of like a depiction is, well, it's like they're going, you know, down into the well or something. But that's not what I'm really thinking. This is up here. Space-time is flat. A gravity sink, I say defined for a sink really, is a place for receiving energy within a system. I mean, that's pretty generic. Again, you can use that for electric circuit too and other things, I'm sure. But I mean, it's a place for receiving energy. And I think that's what's going on. The energy, you know, within the system and spread out over the solar plane, that energy, gravitational energy, is being pulled in to, you know, what is, I would call the sink, that's actually up within the large, massive object in the middle here, and that's the star. So that's basically what's happened. So you can put gravitational energy within a system, right? Just as you can put electrical energy or whatever in the system. So that's a gravity sink. Let me get another coffee here. This, I thought I'd throw this in here just for a little more explanation. But we've all experienced the kitchen sink, right? And we know that a kitchen sink is a basin and it has a drain to it, right, in the middle. So this is somewhat of an analogy, but if you have, we've all seen it, if you have a sink filled with water and a drain, and you pull the drain plug or whatever, and the water gets low, but after it gets to a certain point, you can actually see the water drain in along the basin, the bottom of the basin, and then go into the drain. And that's what I'm sort of getting at here, which is the same thing I'm getting at over there, right? It goes, this attractive force, right, which is a large mass, is responsible for the gravitational field, but it just kind of pulls it in, pulls the objects in to that gravitational field, just like the water kind of gets pulled into the drain. It's the same idea, right? Well, yeah, but a star, except a star core is not unidirectional, right? In other words, I'll do that in a second, but that's the idea of it, right? That the star itself, in this case, I mean, there's a lot of variations that you could do on this. You'll see as I get through it. I mean, I only have 3 whiteboards. I can't go over too many variations here. But this is the whole idea. The drain, of course, is like down there. A star is up there, and that's where the drain. That's actually where the drain is. Unlike a kitchen sink drain, right, it goes down, or a bathroom or something like that. The gravity drain is the star itself. It goes into the star. So that's what's happening. I said like a whirlpool or a tornado. We've all seen them. That's not what I'm getting at, though. I mean, that's the idea of, right? It tracks look at a tornado, it tracks all kinds of garbage and stuff, right? But it's not that. It's within, it would be like if there's just a star or a large object at the top, not just a tornado. So I think that sort of covers a little bit of what I wanted to get at. Let me do the next panel. If you see here what I'm getting at, right? You can see it looks like a little tornado. That's the sink, right? I call it the gravity sink, and if this were the gravity. But you can see it's sort of unidirectional, right? One up, straight up and down. A star can't do that, right? A star is omnidirectional, right? It has like the planet Earth. It has gravitational force all around it. Some has stronger gravity, some has less gravity, but they all have it all comes into the object. And that's what I'm trying to get off here, is just that the star's core, I call it a sink, gravity, I mean, it can come from all over, not just, unidirectional, it's omnidirectional, so you have to keep that in mind, right? Everything's coming in, like the planets here, even if they're in motion, I mean, they're sort of coming in on the solar plane, but you have sort of like what you could call the north, maybe the south. Gravitational fields are still attractive at that area. So, yeah, so, well, go to over here. So this is a star. Well, yeah, here's another view of what's going on. You say, well, that looks like a black hole. It does look like a black hole, but that's not why I'm using it as a black hole, right? It's the same idea. Here's the star. Here are planets on the solar plane. Again, it's as if, right? This is a depiction only, right? It's as if you had that sink where the energy came in, and you could call this a black hole. They did before, right? Call this a black hole where the energy goes in and it sets up a event horizon here. No, that's not my point. My point is, as if the energy, all that energy is forced downward, like these planets, as they come in, they're like sort of like this, going down into it, but they don't. Again, it's a flat plane, and all this energy is incorporated into the massive object itself, some star or star system or whatever. So that's all above up here, right? This is a depiction only, and again, as if. So this is Einstein's curved space, view of curved space. I want nothing to do with that. It's wrong. I mean, over here, if you had like this Einsteinian view, you'd have like this, this would be like an onion, right? You have this onion and then you have all these layers around it. That's not a very good view. And a gravity well underneath here, that's not a very good idea. So mine goes, I mean, it's the core basically of the inside of the star that is represented here, but it's in a flat plane up here again, right? All the energy that is doing this, sort of like pulling it down, is actually pulling it from the inside here, right? That's where the energy sink is, it's inside. I don't agree with Mr. Einstein's general theory at all, and I don't think it has anything to do with reality. And they've seen black holes like this, and they say an event horizon. But that's only true if Einstein's general theory is correct, with space-time. If you don't have space-time, and I don't think there's space-time, as Einstein had stated it, then what you're going to have is you wouldn't have an event horizon at all. If a star actually developed into a black hole, right, it would just be by itself somewhere, just sitting there, and you'd never see an event horizon. There would be absolutely no event horizon. It's just like a star sitting there out in space. There's a gazillion of them, right? But if it's a black hole, you won't see it, obviously. But since I don't think space-time exists in the sense of either Minkowski or Einstein, then you wouldn't have an event horizon. So if somebody comes to you and says, here's a black hole, because look, we can't see the black hole, but here's an event horizon. Right. No, it's not. If it has an event horizon, it's not a black hole. I don't know what it is, but it's not a black hole, because a black hole would not form like that. You wouldn't see it like that. Okay, now that I killed that idea, and then this is what gravity works through matter or space, right? So we can look at the planets today around our sun and we say, well, where's gravity? Well, gravity is there because when the solar system was forming, right, I said before, the planetary nebula, the gravity was all spread out. Some of it became mass onto planets, but what was left is still the gravity. The gravity is still there between the planets or the sun and planets or whatever. So this is sort of what the idea is getting at. If this was a large gas star, let's say, and if that planet was on the periphery, like of the sun itself, well, let's say you were on Earth and there was a man on the surface of the Earth, and you can say, oh yes, I see gravity. Gravity easily, it comes from the center, it pulls it has a pulling motion down. I can see that. But even if that star was compressed into a small ball, right, and the person was no longer on the surface but was at the same point in space, you'd still have the same gravitational field. It would still be there, within reason. So that's the only, no matter how big it is, right? This, I think, goes back to Newton's about point, right? If you want the gravity, you can use the point, the center of an object, right? So even if the material for the gravity isn't there, it's still there. The gravitational force is still there, and that's basically all I was trying to get to. And sort of here's a good question: the chicken and the egg. What came first? And if there's an answer, the answer would be they developed together, right? And the same with gravity and the objects. They sort of just developed together. So some of that gravity that was holding together the spans between the early solar system